In this video, we'll continue our discussion of section 14.6, triple integrals. This is going to be finding volumes using a triple integral. They're going to give us a bunch of equations to bound a three-dimensional area in threes, and that's redundant, but a space in a three-dimensional region in three space. There we go. Still kind of redundant, but we still have this, and it's defined. The way they're going to do it is they'll give us a surface and then some restrictions. The surface itself is a restriction, but it's the up and down restriction. This is the part that we're going to have to figure out is all this other stuff. Okay, so looking at this, we are bounded. We have some kind of shape, and I always draw the xy plane, and this is going to be key to where we're going with everything in this class. Okay, I know I can't do the z's. Z would be, okay, if this is my xy, z equals 0 is this plane. So I know it's this plane and above. And then I know that it's going to be caught between y equals 0. Okay, y equals 0 is this flat line. Right, that's y equals 0. We also can do y equals 2x, so I'm going to do that. I got 1, 2, 3, right? And then we're going to have this bounded region here. And I think we're forgetting something here. Oh, no, and I'll show you how to get this bound. Okay, so this is a slope of 2. Going up that way. And we actually don't, I'm going to leave that off for a moment and just do this. There's y equals 2x. And the problem is right now, okay, I know it's bounded on the plane itself, down on the screen itself. Then I have these two red lines, and I know I'm going to be like, I'm going to have this region in here, but I got to figure out where is it bounded. And they didn't give me anything to tell. So what I do is I can take that surface equation right here, and that plane, the xy plane, happens when z is 0, right? That is the xy plane. So I'm just going to plug in 0 and solve. And this is going to give me my other x bound. So x squared equals 9. So x is plus or minus 3, but we only have one of those options, so it actually bounds it right in there. So we're trying to find the volume that is above this triangular region right here. Okay, so how we set this up. We're going to have our volume. Right? We can do it in any order that we want. First thing I always do is my surface first. Usually that's my z. I know that the surface is caught between 0 and 9 minus x squared. Right? Then I know from there, if I do my z's, now I'm looking at my y's. And y is caught between, if I look at this, I have this lower curve, upper curve. It's caught between 2x and 0. So y equals 0 for the bottom, y equals 2x for the top. And then the x's are great. It's always just whatever the numbers it runs between. 0 and x equals 3. That's here to here. There we go. And then we put in, it's like, what goes in our argument then? Well, just each bound, but make sure they make sense. The z's on the inside, the y's on the middle, and x is on the outside. I'm going to leave it at that. We're going to do a lot of that in this section. It's just setups. So that's how you find the volume. I'm not going to do the triple integral because I gave you 2 examples of those. I feel like those are pretty straightforward. So let's go ahead and get a few more examples in this video. All right, we're going to set up a triple integral for the volume of a solid bound between that surface, z equals that, and z equals 0. All right, well, let's figure out what it looks like when z equals 0, right? That's my xy plane. XY plane, z equals 0 will give me 0 equals the square root of 1 minus x squared minus y squared. If I take the square of both sides, I get 0 equals 1 minus x squared minus y squared. And this gets me x squared plus y squared equals 1. That is a circle. So I know, sorry I'm at an angle the way I write on my iPad. On my plane, I have some type A circle. That fits on the x's like that with a radius of 1. All right, so we know that that is caught between. So we're going to try to find the volume that is between that flat plane, what I have on the screen, and the surface above. All right, to do that, so I know that z is caught between 0 and that surface. Okay, I also know that y, and this one's a bit weird, but if I solve this equation, x squared plus y squared for y, I get y equals plus or minus the square root of 1 minus x squared. That's solving for it. The positive 1 minus x squared is the top, and then minus 1 minus x squared is the bottom. So we know that y is between negative square root of 1 minus x squared and the positive. And then x, we just do the numbers. All right, the numbers run from negative 1 to 1, right? This x to that x. All right, this sets up my integral for volume. I have 3 integrals. Right, I have x is negative 1 to 1. I got y is negative square root of 1 minus x squared. It's a positive, the same thing. The z is z equals 0 to z equals, square root of 1 minus x squared minus y squared. And then we just make sure our bounds make sense. I almost put z again. All right, we don't have an argument. This is how we set these up. That will capture all of the volume of that shape. So pretty nice. The hardest part is setup. That's why we're focusing on it. I got one more setup problem. All right. This one's not as straightforward. It looks straightforward. Set up a triple integral for the volume of the solid bounded by the cylinder above. Okay, so these rules here above. All right, so above, bounded above by, so that this thing is above, and then below tells me this thing is below. Okay. First thing I want to snag is I want to know when they intercept each other. So they're both equal to z, so we can set them equal to each other. All right. I'm going to solve to figure out what the shape is, because this is going to tell me what in that plane where they intersect, what that looks like. So I get 4 equals 2x squared plus 3y squared. If I divide everything by 4, I get x squared over 2 plus y squared over, this is going to be 3 over 4. This is actually a trick here. You can do 4 over 3. This is an ellipse. All right, remember with the ellipse, all right, we'll have, sorry for the crookedness, square root of 2 out here, negative square root of 2, square root of 2. And then also in the y direction, we'll have 2 over the square root of 3. Remember, we take the square root, and then we'll have some type of ellipse like that. Sorry for my bad drawing there, but you get the point. All right, so we are looking at graphing finding the surface or the volume of the surface caught between this ellipse and above, whatever the ellipse is that is above and below. Okay, so when we set this up, volume is bounds. All right, I have up, and the problem is okay, I have z, and then what if we figured out below? Z is x squared plus 3y squared. If you're ever unsure, pick an x and a y and plug it into both and see which one gets you the bigger number. That'll be your top one. All right, so I know that's dz. All right, now I have this equation here, 4 equals 2x squared plus 3y squared. I would really like a y equals to a y equals, so I'm going to solve for y. All right, I got 3y squared equals 4 minus 2x squared. Then we're going to divide by 3. So I got 4 minus 2x squared over 3. Now that square root is going to give me a plus or minus, which tells me that y has to be between the positive of this, square root of it, and the negative. I know what y is equal to both of those, so I know that it is getting, because this tells me the plus or minus, right? Y equals plus or minus the square root of 4 minus 2x squared over 3. that means that it intercepts on both of those and everything in between is caught, right? We're looking at this ellipse. The y's are caught between those. So that actually gives me what I need here. So this is, I'm going to zoom in and try to write it, negative square root of 4 minus 2x squared over 3. And then to the positive 4 minus 2x squared over 3. Okay, so we caught those bounds. Sorry, I had to zoom in to get it fit. And then x is on the screen there. It's between negative root 2 and a positive root 2. All right, we covered it all. We just need to make sure our bounds are there. Sorry, it's all scrunched up, but you can see it there. This is how we find a volume. These are pretty difficult to set up. So more than likely when you are testing for me, it will be some type of setup. Maybe not an evaluate, but just here's the problem. Please evaluate it. Set it up. Don't evaluate. There may be some that I allow calculator, stuff like that. More than likely, I won't have you do any crazy integrals outside of the sections before this. Meaning going forward, all your integrals are going to be pretty tame. The hard part is going to be setting them up.